Detect loop in linked list. This question came up during my on-site at Amazon. What looked like a simple linked list problem turned out to be a test of whether I understood Floyd's cycle detection algorithm, something a lot of candidates overlook. And over 40% of candidates freeze on this logic. Today, we'll make sure you never get tripped up by a sneaky loop again. Let's crush this blind 75 must-know with a foolproof strategy. First, let's break down the problem. Given the head of a singly linked list, we need to determine if there's a cycle, meaning, does any node link back to a previous node instead of ending with null? As you see in the image, node 5 points back to node 2, forming a loop. If there's a cycle, we return true. If not, we return false. It's that simple. Let's assess our options. One brute force way is to remember every node we've seen using a hash set, but that needs extra space, ON. Is there a slicker way? Yes. The classic tortoise and hare method uses 2 pointers. One moves 1 step at a time, slow, the other moves 2 steps at a time, fast. If there's a cycle, fast will eventually catch slow. If not, fast will hit null. This technique gives us ON time and O1 space, super efficient. Now, let's structure our approach. Start both slow and fast pointers at the head. Move slow by 1 node, fast by 2 nodes each loop. If at any point slow equals fast, we found a cycle, return true. If fast hits null, the end, there's no cycle, return false. Now let's solve solution 1, detecting a cycle in a linked list using a hash set. We'll go line by line, see how we track visited nodes, and understand how to detect a cycle efficiently. Time complexity is ON, where n is the number of nodes in the linked list. Each node is visited at most once. The idea: maintain a set of visited nodes. Walk through the list node by node. If we see a node that is already in the set, a cycle exists, so return true. If we reach the end without repeats, there is no cycle, so return false. Think of it like putting a name tag on each node you visit. If you ever see a node with a tag, you know you visited it before. Line by line explanation of the code. We define a class solution to hold our method. This function takes the head of a linked list and returns true if a cycle exists, otherwise false. We create an empty set to store all nodes we visit. Sets allow fast membership checking, like a checklist. Cur will point to the current node we're examining, starting at the head. We loop as long as cur is not none, that is, until we reach the end of the list. We check if this node has already been visited. If yes, it means we've looped back, a cycle exists. If the current node is already in the set, we immediately return true. The linked list has a cycle. If the node is new, we add it to the set. This marks the node as visited. Move cur to the next node in the list. This continues the traversal. If we reach the end without seeing a repeated node, we return false. No cycle exists. And that's how this algorithm works. It first initializes a set to track visited nodes, then iteratively checks each node while moving forward. Efficient, simple, and elegant. Time complexity is ON, as each node is visited once. Space complexity is ON, because we store each node in the set. This is a simple and intuitive way to detect cycles. An alternative is the 2-pointer method, Floyd's tortoise and hare, which uses O1 space. Let's check if our hasCycle function works. We want to see if a linked list contains a cycle, where a node points back to a previous node instead of none. We test it with 3, 2, 0, -4, and pos equals 1, meaning -4 points back to node 2, forming a cycle. The function uses a set to track visited nodes. As we move through the list, we add each node to the set. When we reach a node already in the set, we detect a cycle and return true. The output is true, confirming the function works. This implementation correctly detects cycles in any list, is simple, and efficient with ON time and space. This solution detects a cycle in a linked list without using extra memory. It uses 2 pointers, one moving slowly and the other moving faster. If there's a loop, the fast pointer will eventually meet the slow pointer. This is also called the tortoise and hare algorithm, and it's very space efficient. Time complexity is ON, where n is the number of nodes in the linked list. Each node is visited at most once by slow and fast pointers. Define a class solution and the function has cycle. Start with both slow and fast pointers at the head of the list. Slow moves step by step. Fast moves twice as fast. Keep looping as long as fast and fast.next exist. If fast hits the end, there's no cycle. Move slow by 1 node, and fast by 2 nodes. Think of it like a tortoise and hare racing around a track. If slow and fast meet, there is a cycle. The pointers have collided inside the loop. If the loop ends without a collision, fast reached the end, and there is no cycle. Return false. Slow and fast pointers ensure ON time complexity. No extra memory is needed, O1 space. This algorithm detects cycles elegantly without modifying the list. Now that we've implemented our solution to detect cycles in a linked list, let's see it in action. We test it with 1, 2, and pos equals 0, meaning node 2 points back to node 1, forming a cycle. The function uses 2 pointers. Slow moves 1 step at a time, and fast moves 2 steps. If a cycle exists, fast will eventually meet slow. Otherwise, fast reaches the end. For this input, slow and fast meet, confirming a cycle. The output is true, showing that the implementation correctly detects the cycle. This 2-pointer approach efficiently identifies cycles, works for any list, and is simple, accurate, and reliable. Breakdown recap. Conceptually, we're given a singly linked list, and we need to determine if it contains a cycle, that is, if any node points back to a previous node instead of ending with null. If a cycle exists, we return true, otherwise, false. Assess recap. We looked at different approaches. A brute force method is to store visited nodes in a hash set, but that uses extra space. A more elegant solution is the tortoise and hare technique, 2 pointers moving at different speeds. If there's a cycle, the faster pointer eventually catches up to the slower one. If not, the fast pointer reaches the end of the list. This method gives ON time with O1 space, highly efficient. Structure recap. Our approach was straightforward. Initialize slow and fast pointers at the head. Move slow 1 step at a time, fast 2 steps. If they meet at any point, a cycle exists, return true. If fast reaches null, no cycle exists, return false. Implement recap. We implemented this using the classic 2-pointer method. Running it on LeetCode, the code executed cleanly, detecting cycles or confirming acyclic lists without errors. Check recap. We verified it with multiple cases. Lists with cycles, like one where node 5 points back to node 2, correctly returned true. Lists without cycles returned false. This confirmed that the logic works as expected in all scenarios. Closing insight. The key takeaway? Cycle detection is all about pointer strategy. By carefully moving slow and fast pointers, you can catch loops efficiently, using constant space,